Good evening, and probably the last serious talk for today. Yagmur will talk about if machine learning can improve JVM performance. You're welcome.
Thank you. Hello, everyone. Welcome to my quick session about how can machine learning assist to improve JVM performance. I would like to start with a picture. This was taken exactly 1 year ago, again at JFocus. That's me in the center, volunteering and thinking how amazing the event was, along with all the inspiring speakers. Back then, I was still in my master's program at KTH here in Stockholm, and working on my master's thesis in collaboration with Oracle's Java Platform Group. This was an exciting project, and in the end, we got promising results that make the idea worth sharing with you today. First, let's make the problem clear. Do you know how many JVM flags there are, or have you ever printed all of them? I can show you how. By using the print flags final option, we can see all the flags and their values. Some related to compiler, some control memory settings that we can set to reasonable values, and some are just binary flags that we can set to simply true or false and so on. Do we need to use all of them? No, we don't. But if we care about our program's performance, by performance I mean throughput and latency, it might be helpful to be aware of these flags. For example, adjusting some memory-related flags could improve the performance. But how are we going to know which values are the best? Unfortunately, it is not an easy task. So, can machine learning help us find the optimal flag values that maximize throughput and minimize latency? Let's find out. So this was the problem we addressed in my thesis, and now we will talk about the main steps that I followed. First, we need to select some Java applications that we can measure their performances accurately. And for that, we use some of the popular benchmarks like SpecJBB 2015 and Da Capo, as some of you may already know. Then we need to collect some data and process it to train the machine learning model. But hold on, what is the data? From what data will the machine learning model learn and tell us the optimal flag values? Garbage collection logs. But why garbage collection logs? Because they have some cool information about the usage of the memory during runtime. We can enable GC log generation with this JVM flag. In our work, we used G1 as the garbage collector, and here is an example snippet from G1 GC log. To create the dataset, we parsed it to extract all this information, like timestamps, GC ID, garbage collection calls, size information of different regions, and so on. You can read the details of these in my thesis if you want to know more. But one important point to highlight here is the young generation, old generation terminology for G1. Many of you might be already familiar with it, but for those who are not, basically, young generation is the region, the memory region, where the objects are stored whenever they are created. And if they survive long enough, I mean like several GC cycles, then they migrate to old generation region. This detail is important to understand the JVM flags that we select to optimize. So for our experimentation, among all those flags, we selected 2 G1 garbage collector flags to understand their functionality. Let's imagine this is our Java heap, which is allocated from 0 to 100%, and some part of this heap will be used for young generation. And by default, this is maximum up to 60, minimum up to 5% of the heap. And we can control these boundaries with these 2 JVM flags. So we focused on these 2 flags to find optimal values for them to improve the performance. In other words, we played with the young generation sizing within the heap. However, we need to consider the throughput and latency improvements separately, since there's a trade-off between them. Therefore, first, with the minimum young generation percentage flag, we believe that we could control throughput as it affects the frequency of the garbage collection events. Then we investigated whether the maximum flag could improve the program responsiveness or latency without affecting the improved throughput, because it affects the time spent on each GC event or the GC pause times. So far, we have collected the data, we know which flags to tune. Now we need to process the data and do some feature engineering so that our dataset can be ready for training. The machine learning model needs to capture the mathematical relation between the memory sizing for young generation and the overall application performance. The model will get insights about how all the objects are created, moved, stored within the memory, and how all these information affects overall output performance. To help models to capture this relation, we used sliding time window approach to preprocess our data. Once the GC log is parsed and the features are extracted, we obtain tabular data. And here's a simplified visual with some dummy values to illustrate the concept. Each line represents a memory state at a specific timestamp, with the memory-related features organized in columns. We can define a time window of, let's say, 1 millisecond that encapsulates the lines where their timestamps sum up to 1 millisecond in total. Then we do some feature engineering, such as calculating new features, averaging the feature values, and finally create the preprocessed data. As you can see in the final dataset, each line represents the preprocessed data from each time window. Now the dataset is ready to train a machine learning model. The third step is to select a model. In the thesis, we explored several models, but in this presentation, we're going to talk about only one, which is Gaussian process regression. So the goal of training a model is to discover the relationships within our data so it can predict outcomes for new and unseen data. In our case, we are performing regression task, and we are using a Gaussian process to accomplish it. Regression is used to find a function that closely represents the underlying relationship within the data. In other words, it is fitting a mathematical function to the data. However, there are infinitely many possible functions that could fit the same data. Gaussian process is a probabilistic method that represents a distribution over possible functions, like a cloud of curves that could fit the data. The true function is likely to lie somewhere within this cloud. It identifies the most likely function under the assumption that the function values for any set of inputs follow Gaussian distribution, which is represented by this formula. We don't need to dive into the math here. It just helps connect the concepts we are discussing. So now let's see this with an example. Imagine these red dots in the graph represent some observed data, which can correspond to the values that we extracted from GClog in our case. And the dashed black line represents the true but unknown function. So our goal is to find patterns within our data and predict the young generation size that optimize performance. But as we mentioned, there are infinitely many potential functions that could fit this red data. So Gaussian process regression calculates a confidence interval, or the cloud of curves, where the true function is most likely to lie based on the observed data and the assumption of an underlying Gaussian distribution. So the blue line represents the most likely function, and the shaded area around it represents the confidence interval, or the range where the true function is most probably located. As next step, we first tune the hyperparameters of the model. For those who are unfamiliar with the hyperparameter term, it is a configuration parameter that we set before training that controls the learning process. Then we do some training and testing, nothing fancy here. However, for prediction, selecting the inference data is critical for models to understand the prediction objective and provide outputs that improve specific aspects of the application performance. To create the inference data, we select the data points with the worst performance-related feature values. For throughput, we maximize the time spent for only application in each time window, excluding GC pauses, for those data points. With this, we use the model to predict flag values that maximize throughput. And for latency, we aim to minimize the maximum pause times per window. So we kept the values exceeding a certain threshold to help models predict values that minimize overall pause times. And finally, as the last step, we set the flags to the predicted values and make a comparison between this run and the run where we did not use those flags. So with the steps 2, 3, and 4, we have been actually designing a machine learning pipeline. If we consider the whole procedure like a black box, the input to the black box is the GC log that we generated from our Java application, and it outputs the predicted values for the flags that we desire to tune. So this pipeline is the core implementation of this work, so let's put the pipeline stages into a diagram. First, we begin with some feature engineering, parsing the GC log, and preprocessing this information with the sliding time window approach. Then we train and test our model, and we form the inference data by relying on the net application time for throughput improvement and the maximum GC pause times for latency. And the pipeline outputs the predicted flag values. Now let's see this, the place of this pipeline in our overall workflow diagram to make the bigger picture more clear. And here is a simplified version of it. On the left, we have our Java program. We run it once to generate the GC log, and then we feed that GC log to our machine learning pipeline, which gives us the suggested flag values for the flags that we selected. And eventually, we are comparing the performance of the run, where we use the predicted values, and the default run, let's call it like that, where we did not use those flags. Now, I want to share some results of a program from the capo, where we applied the predicted values. For the rest of the results, you can refer to my thesis. We set one flag at a time, starting with the minimum percentage flag, and we are comparing the means of multiple runs of each combination. Let's remember there's a trade-off between throughput and latency. So when we set only the minimum young generation percentage flag to the predicted values, we see that the throughput of the application improved by 20.6%. However, the latency got worse by 1.5%. Then, by setting the maximum percentage flag as well, we see the throughput drops slightly to 20.3%, better compared to default. And we managed to have 3.46% better latency. If you remember, our goal was to control the latency with the second flag without affecting the improved throughput much. And this is very promising. Maybe one can achieve that much improvement for all other Java applications, or even better. To conclude, I shared a novel approach to using machine learning for JVM tuning, with the purpose of inspiring and providing a path for those who are interested in this field so that they can try out other garbage collectors, flags, models with a similar approach. And the key takeaway here is that GC logs hold valuable insights, and a well-performing machine learning model can assist users in selecting optimal JVM flag values, even without requiring a deep technical knowledge of JVM internals. So, if you are interested, check out my thesis. Also, I would love to hear your feedback, both for myself, and I think in this QR code, you're going to find the rating link for the JFocus as well. I hope you enjoyed and learned some cool things from this session. Thank you.
Amazing, thank you.